In this part of mechanical properties of fluids, we will study about Pascal's law in detail. Pascal's law. Pascal's law tells us how pressure can be transmitted in a fluid. It can be stated in a number of equivalent ways as the pressure exerted at any point on an enclosed liquid is transmitted equally in all directions. Secondly, a change in pressure applied to an enclosed incompressible fluid is transmitted undiminished to every point of the fluid and the walls of the containing vessel. And in another way, you can say the pressure in a fluid at rest is same at all points if we ignore gravity. For its proof, we have to use two principles. Number one, the force on any layer of a fluid at rest is normal to the layer, and Newton's first law of motion. As shown in the figure, consider a small element ABC, DEF in the form of a right-angled prism in the interior of a fluid at rest. The element is so small that all its parts can be assumed to be at same depth from the liquid surface, and therefore the effect of gravity is same for all of its points. Suppose the fluid exerts pressure PA, PB and PC on the faces BEFC, ADFC and ADEB respectively of this element, and the corresponding normal forces on these faces are FA, FB and FC. Let AA, AB and AC be the respective areas of all the three faces, and in right angle triangle ABC, let angle ACB is theta. As the prismatic element is in equilibrium with remaining fluid, by Newton's law, the fluid force should balance in various directions. So, for horizontal direction, FB sin theta must be equals to FC and FB cos theta along vertical direction must be equals to FA. And from geometry, AB sin theta is equals to AC and AB cos theta equals to AA. And by dividing these, you will get FB by AB equals to FC by AC equals to FA by AA. That means the pressure at point B equals to PC equals to PA. Hence, pressure exerted is same in all directions in a fluid at rest. It again reminds us that like other types of stress, pressure is not a vector quantity because no direction can be assigned to it. Conclusion: for a uniform fluid in equilibrium, pressure is same at all points in a horizontal plane. This means there is no net force acting on the fluid and the pressure is same at all the points. A fluid moves due to the difference in pressure. That means fluid will always move from a point which is at higher pressure to the point which is at a lower pressure. For example, blowing of wind. Wind is nothing but moving air. And air is a fluid, so the air moves from the region of higher pressure to the region of lower pressure. Variation of pressure with depth. For this, consider a fluid at rest in a container as shown in the adjacent diagram. Point 1 is at a height h above a point 2. The pressures at points 1 and 2 are P1 and P2 respectively. Consider a cylindrical element of fluid having base area A and height h. Because the fluid is at rest, the resultant horizontal forces should be zero and the resultant vertical forces should balance the weight of the element. The forces acting in the vertical direction are due to the fluid pressure at the top, P1 into A. Acting vertically downward, and at the bottom P2 into A acting vertically upwards. That means P2A minus P1A will be equals to mg. Now, if rho is the mass density of the fluid, then the mass of the fluid will be rho into volume. That means rho into h into A. Therefore, P2 minus P1 equals to mg will come out rho gh. Pressure difference depends on the vertical distance h between the points 1 and 2, mass density of the fluid rho, acceleration due to gravity g. If the point P1 under discussion is shifted to the top of the fluid, say water, which is open to the atmosphere, then P1 can be replaced by the atmospheric pressure and P2 by P. Then we can write simply P is equals to PA plus rho GH. Thus the pressure P at depth below the surface of a liquid open to the atmosphere is greater than the atmospheric pressure by an amount of rho GH. And this excess pressure, rho GH, is known as gauge pressure at that point. The height of the fluid column is important, and note the cross-sectional area or base area or shape of the container as from the equation P is equals to PA plus rho GH. That means the liquid pressure is same at all points at the same horizontal level or at the same depth, and this result is appreciated through the example of hydrostatic paradox, which we will study in the next part.